I'm Vaivaswatha, and I'll be presenting pliron today. Pliron is an extensible compiler written in Rust. So this is the outline for my talk today. I'll begin with a brief introduction to what extensible compilers are, just for some of you who may not be familiar with MLIR. And then I'll talk about why I decided to write pliron, and then discuss some design details of the project itself, and finally end with where pliron stands today and what I plan to do in the future. Okay, sorry. Okay, so let's look at traditional IR like LLVM IR or Gimple. LLVM IR has about 70 opcodes, and Gimple has about 30 opcodes. And by opcode, what I mean is instructions such as load, store, or addition, subtraction, and so on. And what this means is that what can be represented in the IR is restricted to just these. Now, suppose there's a compiler engineer who's building a compiler for something non-traditional. Maybe quantum computing, or even something like wanting to represent higher level language constructs within the IR. It's not easy. I mean, you can't do it without hacking into the core of the compiler and making a whole lot of modifications. So, and this is where MLIR comes in and says, I provide you a library, you use MLIR as a library, but you can define your own operations, you can define your own types, and the rest of the compiler infrastructure, the data structures, algorithms, all of that, they just come for free. Now, a consequence of this extensibility property is that MLIR is quite big. Just the repository has about 50 dialects and more than 500 operations. And this does not even include, what can be defined out of the tree and when MLIR is used just as a library. Now, the question is, in such a scenario, how would you write a traditional compiler analysis or a compiler optimization? Just to drive the point that I'm trying to make, let's look at an example. What we have here is a simple function that checks whether an instruction can be dead code eliminated. What it first does is see if does this instruction have any SSA use? That's obvious. If there's a use, you can't remove it. And then it checks is it a store, is it a call, and so on. What that means is, does it have any side effect? That's what it's trying to check. Now, the problem is, in an extensible compiler, when someone's writing, when someone's using the compiler as a library, he may be defining more operations outside of it. And when you're writing an algorithm like this, you have no way of knowing all the possible operations at all. And how MLIR solves this is, and it's a good solution, is we use what are called interfaces. These are very similar to Java interfaces or C++ abstract base classes. And the idea is that you don't express semantics using the hard concrete opcode, but instead you use interfaces to express these semantics. And basically pseudocode, and how you would rewrite the previous function would be, you check if there's an SSA use that's the same as before. And then what you do is you see if the operation in question implements the side effect interface. The interface is shown above, and it just has one method that has, may have side effect. It returns true or false. And now, if the operation does not implement the interface, then you've got to be safe. You don't know anything about it, so you say, don't eliminate this. We should play it safe. But if the operation does implement the side effect interface, you can just ask the operation itself through that interface and act accordingly. And that's interfaces, and that's kind of at least the way I understand MLIR or extensible compilers. And now a brief motivation. Why did I decide to write pliron? We all know Rust. At least you're familiar with it. Rust is a pretty popular systems programming language with certain guarantees on memory safety. And I, as a compiler engineer who's been working with Rust for the past couple of years, when I wanted to use an extensible compiler, I had two choices. One is use MLIR through its C bindings, and the other was to re-implement all of it from scratch in Rust. And what I decided to do is the latter, and in the next few slides, I try to justify why I decided to do that. Okay. Memory safety. What we have here is a simple program written in Rust using MLIR's C interface. And all that it's doing is setting up a context, and then it creates an empty module, it prints the module, it clones the module, and then prints the clone. That's all it's doing. And when you run this program, this is the output that you see. There are 2 empty modules printed. So far so good. It all looks good. But the problem is, the compiler is a pretty big infrastructure, and somewhere in between, let's say you end up creating a dangling pointer. And that's what happens there, MLIR operation destroy. And then, well, on a release build, it's hard to say what will happen, but on a debug build, this is what it prints. I have 2 problems with what's happening here. The first is that the assert message that you see, it says, cannot clone region into itself. That has very little to do with the problem that we actually have, which is a dangling pointer. It doesn't indicate to the actual problem. And then there's an even more critical problem, which is that there's an empty module that's actually printed there. It has a different syntax from what we saw in the previous slide, but it's still valid MLIR syntax, and it's printed. Now, when someone's debugging this sees it, he's kind of going to be misled because, well, the module is being printed, so he's going to be looking for the bug in the wrong place. And well, especially for a Rust programmer who has little knowledge about C++ or even little knowledge about MLIR internals, this is going to be a nightmare to debug. The second problem is type safety. When you use MLIR through its C++ interface, it's all nice and good. Good, nice, rich C++ types. So as an example, if you want to just get the bit width of an integer type, all you have to do is call that method in the integer type object. But when all of this translates to the C interface, all you have is a common type called LLVM type ref. And now if you end up passing one of these other types, the type checker doesn't catch it, and that's, the whole arrangement is basically letting you shoot yourself in the foot. And the last problem is that the C interface is really designed to use the compiler, not hack into it or extend it or modify it or any of that, because a lot of features that are there in the compiler are not exposed in the C interface. So at least for me, after a little bit of digging in, it was quite evident that Rust, being a good systems programming language, needs an extensible compiler infrastructure. So we'll now look at some design details of pliron itself. Let's start with graphs in Rust. Rust's memory safety guarantees primarily comes from its borrow checker. The borrow checker is a static analyzer or static checker that enforces certain rules on the program that the Rust compiler is compiling. And the 2 rules that it has is when you have an object, you can either have one mutable reference to it, or you can have any number of immutable references, but not both. And the second rule is that all references must always be valid. You can never have dangling references or dangling pointers. But now the problem is that if you want to represent a graph with these constraints, it's hard. If you do something like this, how you would do it in C or C++, the compiler is just going to reject it. And what most Rust compilers do is use arenas. This actually came up in the Q&A on one of the talks yesterday. And in particular, pliron uses a generational arena. A generational arena is really just a vector from which you allocate objects and free objects back to it. And instead of references or pointers, you just use vector indices. The additional memory safety that it provides is it maintains a generation counter for each array slot. And whenever you deallocate an object, that generation counter increases. So if you end up having a dangling pointer or a dangling index in this case, it's just going to immediately panic. And in addition to using generational arena, what pliron provides is a type-safe wrapper around these indices, just so that you don't mix up the index for an operation with the index for a basic block. So that's what that type-safe wrapper that you see around there is. And next, the fundamental building blocks of a compiler. Operations, types, attributes, all of that are there in pliron. They all work. Some points of interest. We use linked lists for representing blocks in a region or operations in a block. This might, kind of come as a surprise that I'm even mentioning this, but the reason I'm doing that is some Rust-based compilers, including Rust itself, uses vectors. pliron also has always available and always valid SSA diffuse chains. Again, for people using LLVM, GCC, this is not a surprise at all. This is always given, but most other compilers don't provide it. We also have infrastructure for printing and parsing the IR. This is what an operation in pliron looks like. It's very similar to that in MLIR. And then we also have ops, again similar to MLIR, that are just a thin wrapper around operations for that opcode specific methods. We have, well, a type is every SSA value has a type, and types are unique and immutable, just like in MLIR. Attributes are a little different from what it is in MLIR. We don't unique it, and hence they are mutable. This means that they are more similar to the recently introduced or more recently introduced properties in MLIR. And finally, interfaces. We saw how important interfaces are for an extensible compiler. The good thing about using Rust is that Rust has traits. And conceptually, traits are really what interfaces are. So we just piggyback on that. What pliron additionally provides is some macros to annotate a trait as interfaces. And what this allows is to safely cast between an operation object to its any trait, any interface that it implements. And also this allows automatically calling the verifiers on each interface that an operation implements. So this is just an example of interfaces in pliron. There's not much to say here. I'll just let you digest it for a few moments, and then I'll move on. Okay, we're almost about to end the talk. This is where pliron currently stands today. The core infrastructure is there. And I've actually been able to run a proof of concept. Proof of concept LLVM dialect is there, and what I've been able to run is a Fibonacci program end to end. That is, take LLVM IR, put it into pliron's LLVM dialect, back to LLVM IR, and then compile and run it. It works, so that means we can represent that much effectively. I'm still working on having a table gen-like syntax. The plan is to use Rust macros that are quite powerful rather than another whole new language for it. Some common algorithms I'm still working on, and in the future, I want to have a pass manager, pattern rewriter, and the whole stuff. So that's it. Please go ahead and try pliron. Code contributions are always welcome, and even otherwise, just general feedback is very much welcome. And I owe a special thanks to my colleague Vinay, who helped me with a lot of design decisions throughout the project. So I should mention him. Thank you.
So thanks, Vaivaswatha, for this nice talk. Are there any questions with respect to this? So one question is there specifically for MLIR, or is it even for, let's say that is it only for geared towards machine learning MLIR kind of thing, or general purpose?
No, this is this is more of a programming language thing rather than a machine learning thing. Although, even though MLIR is popular for machine learning, even MLIR itself can be used for representing different programming language constructs. So this is based on the same idea, and machine learning is not my primary focus at all, but that could as well be represented here.
And second question is that, let's say that somebody has to write an analysis pass or transformation pass using this thing. Do you already have some template visitors, etc., that one implements some callback interface and it will just take care of? Or
They're partially there. Visitors are there. Tree walkers are there. Uh, they're still not mature enough, but they are there. So we just want more people writing, and then it'll get refined. But plenty of it is already there.
Uh, okay, thanks the speaker one more time.
Hi. Hi, Vaivas. One question from me. Yeah, interesting talk, and I can see that this effort, pliron, I mean, it is a huge effort, and it's.
Sorry, I couldn't
I
hear.
mean, pliron. I mean, your project. It's kind of a huge project because you are trying to build what MLIR is trying to do, and I appreciate your effort. And one
Thank you.
question from me is, you are trying to build MLIR kind of for a DSL for domain specific. Anyone who would like to define dialog and all, they can do that in your platform.
Yes.
Exactly as what they can do it for
Yes.
MLIR.
Yes.
That is what your objective is.
Yes, that's the idea.
Yes. Okay. So why? I mean, you mentioned a lot of things about memory issues and other stuff in what the MLIR infrastructure is. Do you have any other kind of drawback or any kind of limitation of the MLIR infrastructure that you yourself trying to solve? I mean, particularly or in general?
Uh, not really. I didn't start with this because of any drawbacks in MLIR that I saw. Actually, I didn't see any. But the reason is that if somebody with a Rust background wanted to work on this whole thing, there was really not a good way to do that. And at least I enjoy writing Rust code, and I'm sure there are plenty of other people who want to do that. And for all of them, something like this would really be useful. So yeah, that was the idea. But it's not really because of any drawbacks with MLIR per se, except that MLIR is very huge and it's in C++.
Yes. Thanks. Thanks.
Hey, nice project. I
Thank you.
just want to ask, for LLVM C bindings, right? We have a Rust crate like LLVM sys, and on top of, I mean, that's where a lot of unsafe code is. But then there are Inkwell and so on crates existing which use ergonomic Rust to implement the C bindings, right? And then it gets mature. For example, Solang is written completely in Inkwell. So can you just tell about what were the reasons why you didn't chose that path of having this abstraction on C and then going into ergonomic Rust?
Yes. So the kind of project that you said, there are similar ones, although not yet mature, there are similar ones for MLIR also. I think it's called MLIR. That's the same idea where you provide type-safe wrappers around MLIR's C interface. That kind of partially solves one of the problems that I spoke about with using C interfaces, which is the type safety part of it. Yeah. But the memory safety part is still going to be there. And it's still not functionally complete. In the sense, let's say I just want to do, I just want to call dominator, I just want to get the dominator tree for my function. I can't get that from the C interface. It's really exclusive only to the C++ interface. The C interface doesn't even expose it. And the LLVM community is not even ready to. Okay, I'll just give you a very small example. So the get instruction, get element pointer, has a function called get indexed type. So what that function does is compute the result pointer type. And that function is not exposed in the C interface. It's there in the public C++ interface. Mm-hmm. And when I created a PR for it, I was told, why do you need this? I said, if I want to type check the IR that I have on my Rust side, I should be able to do it. And without that function, I'll have to rewrite it. But they didn't agree to it. So, okay. I mean, it's not just feature complete, but it's, again, battling with the community to get a whole lot of features out just so that you can get all of these safety features in Rust.
So it's the deficit on the C binding side which
Yes, at least for the type safety part. But the other two parts, the features and the memory safety part, there's really nothing you can do about it.
On the C side or in the Rust abstraction?
Well, the C example that I showed for memory errors, right? That can as well happen in the C++ code. You don't even need C for that. Even the C++ code, if you have a dangling pointer and it crashes, that's what it prints. So that problem is not going to be solved even in C++.
Okay, thank you.
Yeah, thank you.